Thanks. Well, I'll begin with a word of prayer. Dear Heavenly Father, we thank you for this morning. Again, Lord, I thank you for the students and their diligence. Just pray that you'd just help us this morning to glorify you, learn what we do, Lord. In your name I pray. Amen. Let's see here. So let me just start things out here by just showing you carefully, well, quasi-carefully, the theorems that I just kind of mumbled through at the end of last lecture, because I want these to be a sort of backdrop to a couple of examples I show you guys today. And of course, there should be plenty of time for your questions about the homework too. But before I forget, let me do this, otherwise I'll forget. Come on, stay plugged in. This computer doesn't have long to live. Well, it's going to sit on a desk somewhere and mine Bitcoin for the rest of its existence sometime soon. Let's see here. All right, let's see here. Come on. No, good guess though. I wear the blue shirt with all sincerity. There's nothing wrong. It's all good. Okay. Sorry, I misbehaved. Let's see here. So, you guys already know. Well, hopefully you're coming to terms with what is a subspace. Can you guys tell me in words what's a subspace? It is a non-empty subset, right, of a vector space, which is a vector space with respect to the ambient, with respect to the parent. The superspace is vector space addition and scalar multiplication, right? It's a subset which is also a vector space in the natural way, right? How do we check something's a subspace? We got two ways, right? I guess there's three. The first and least attractive way is just to check all the axioms directly from the definition. None of us want to do that. Option two is subspace test theorem, right? Which means you got to check x plus y and c times x is in the subspace again for all x and y in the subspace, and for all scalars c. You probably noticed by now that computationally, while that's two things, you can accomplish it with one thing. If you just check if cx plus y is in the subspace, then it automatically follows that x plus y and cx are in the subspace, taking the case c equals 1 and y equal to 0. So there's that. And then what's the other way we have this to show things are subspace? If it's a span, right? So that's super nice. Let's see here. So this right here, by the way, if you look at this example, just while I got this out, I'm checking what? I've got t squared minus 1, t squared plus 1, and 4t squared. What am I trying to ascertain here? I'm trying to ascertain whether or not f of t, comma g of t, comma of h of t is linearly dependent or linearly independent in the space of polynomials in t, right? Now, if I followed my advice at last class, what do? I'd pick a basis, I'd find coordinate vectors for these, and I'd do row reduction on the coordinate vectors and then track back through the lemma. Did I do that here? I did not. I just did direct calculation in the quadratic polynomial space, right? And I just found by linear independence of t squared and 1 that the coefficients have to separately vanish, which only gives me two equations and three unknowns. So as you can see, there's C2 as a parameter. Any choice of C2 gives us a non-trivial linear dependence amongst these polynomials, right? So do you need, my point to you is you don't need to do what I outlined at the last class to do these problems, right? For a simple problem like this, do you need to pick a basis and look at coordinate vectors? No, right? So you got to decide whether or not, that's a very serious tool to be using unless the example's got, a little bit more computational teeth to it. It's got to be complicated enough that it's worth doing that. It may never be worth doing that. You can always kind of do this style of things and read off equations and then do row reduction on those equations just the same. I mean, I'm not convinced that the method I showed you at the end of the last class is actually computationally useful for questions I can ask you on a test, all right? But it is something that's theoretically useful. So we talked about a basis, dimension, right? I've given you two proofs that the dimension is well defined. We've talked about coordinate vectors a little bit. And here I have some propositions I haven't stated in class but are kind of common sense, right? Like, for example, if you have a matrix, the pivot columns form a basis for column space of A, right? Because what's the column correspondence property say? It says, if we look at the reduced row echelon form of the matrix, we can build any non-pivot column as a linear combination of pivots, right? So like, for example, this matrix, you row reduce, you get that. That means columns 1, 2, and 4 serve as a basis because we can build column 3 by 5/3 column 1, 2/3 column 2, and first times column 4. You know what else? That column is actually the coordinate vector for column 3 with respect to the pivot basis, right? Because it's 5/3 the first one, 2/3 the second one, 0 times the fourth one, which is the third thing in the basis, if we number them columns 1, 2, then 4. So this not only does it give you a way to find a basis, it actually gives you a way to like read off coordinates if you think through it, yeah? Which is probably not a point I emphasized here, right? A good way to improve this example in my notes would be to add a sentence, hey, by the way, this also shows that the coordinate vector of column 3 is 5/3, 2/3, 0. If we take the basis to be column 1, column 2, column 4. Right? I also show you guys in the notes a method to find the rows which serve as a basis for row space. It's kind of sneaky. What you can do is take the transpose of the matrix, right? Reduce that, and then that will reveal any linear dependence between the pivot rows, well, the pivot transposed rows, and the things, and the, so this will reveal which rows I should take as a basis if I want. Well, in fact, this is kind of a bad example because they're linearly independent. So it's hard to really see this proposition much at work here. They're all pivots, everything you need. The row space is three-dimensional. In other words, this one, though, you see row, let's see here, row 1 and row 3 we should take as pivot. Well, we should take those as a basis because the second row is twice the first row, and the last row is twice the first row plus 1 times the third row, right? But this is a sneaky kind of trick to transpose the matrix, use the column correspondence property on the transpose to reveal any linear dependence between the rows. Again, this is much like the thing I did at the end of last class. It's useful in principle, but in practice, for actual examples, like in state on tests, you can almost always just see linear dependence between rows if you just start looking for them. In your homework, for example, I gave you a matrix with 4 rows. If you just look at it, you'll be able to see that 2 of those rows are linearly independent, and the other 2 can be built from the 2 that you choose as the basis. Which problem am I talking about? 66, yeah, okay. All right, so long story short, if we have a matrix A, the pivot columns can be used as a basis for the column space, and a basis, and well, by the way, also suppose you don't want to do the row reduction of the transpose. Another thing you can do is just look at the reduced row echelon form, or even just the ref of A, which is before we do the backwards pass. Already, when we get to the reduced echelon form of A, it should be clear. Well, you'll have the non-zero rows, right? And those non-zero rows can be used as a basis for row space, even though the rows in this are not in the original matrix. If you're not, in your homework problem, I think I asked you to use the rows in the matrix to form the basis, right? So that's somewhat restricting. That means that you can't use this proposition directly, because this proposition says the non-zero rows in the reduced echelon form of A form a basis for the row space. Now, the reason that this proposition is reasonable is because row operations don't change the row space. What do row operations do? They switch rows, right? They add one row to another. They scalar multiply a row or take a difference of that. all of those things don't change the span of the rows collectively. All right? So the row space of any row equivalent matrix is the same. So anyway, like here, that's the REF. REF is, by the way, not unique. There's more than one possible REF. But anyway, this shows that 1, 1, 1 and 0, 1, 2 can be used as a basis for the column space for that matrix. Right? Well, obviously you get that one. Right? If we want to generate 1, 1, 1, 1, 1, 1 is a good choice. Can I get 1, 1, 1 from a linear combination of 1, 1, 1? Yes. How about 1, 2, 3? Well, that is exactly 1, 1, 1 plus 1, 2, right? So, yeah. But, I mean, just to rain on my parade a little bit here, do you need my proposition to do this example to find a basis for the row space of this? Should you have to do calculation to find a basis for the row space of this matrix? Have confidence in yourself. You can write down the basis. It's the first and the third rows, because the second is clearly a scalar multiple of the first, right? And also, if we look at rows 1 and 3, they're linearly independent, right? So linearly independent, span everything, basis. So the row space here is two-dimensional. All right, let me move on. I didn't want to talk about that the whole time. We'll look at more solution spaces. The interesting thing about this calculation is it shows once and for all that the vectors which appear in the null space answer necessarily are linearly independent. So when you do that thing, you write down the AX equal to 0 solution, and you plug in the equations that you find, right? Then you pull out the parameters, and you have vectors remaining. The vectors that remain have to be linearly independent. If they were not, that implies a dependence between your non-pivotal variables. And that's impossible from the structure of the reduced row echelon form. So it's part of another gift the reduced row echelon form gives to us is linear independence of the vectors which appear when you factor out the null space solution. We'll see it in every example we work, but this is an attempt at proving it. There's probably a better way to prove it. So for example, here's a specific example in case you don't understand what I just said. If we look at, well, this is kind of a stupid example, but maybe it's useful. The matrix A, which is 1, 2, 3, 4, in other words, it is the 1 by 4 matrix, right, the row vector. What's the null space of this? Well, that would be the set of all x such that AX equal to 0, right? So geometrically, what's that? That's the set of all four vectors, which is perpendicular to 1, 2, 3, 4, because A times X is a dot product of row A with column X. But it's not particular. I mean, what's the reduced echelon form of A? It's that. It's already done. Yeah, there's nothing to do. Its leading entry is 1, and there's no way you can change the 2, 3, 4 with row operations, right? So when you look at AX equal, you have one equation, x1 plus 2x2 plus 3x3 plus 4x4 equal to 0. So solve for x1, we get x1 as that, which when we plug it into the generic x, we get this, and then we can factor out the parameters x2, x3, x4, right? And again, these are linearly independent. Here's a more exciting example. This matrix, 3 by 5, right? Row reduces to that. So we have the first 3 columns are pivots, and the last 2 correspond to non-pivot variables, x4 and x5. So we write all of our variables in terms of our non-pivot variables, right? Plug it in, and it gives you two vectors here. Do you guys notice any pattern here? What's the relation? How about the column space? What's the dimension of the column space for this example? 3. What's the dimension of the null space? 2. What is 3 plus 2? 5. But what else is it here? The number of what? Number of columns, yeah. How about the previous example? We had 4 columns? What was the dimension of the column space for 1, 2, 3, 4? Dimension of the column space is 1. Because you can take the number 1, and 2, 3, and 4 are scalar multiples of that. Right? What's the dimension of the null space? 3. So what's the relation? Dimension of null space plus dimension of column space is what? Again, number of columns. Any other patterns you notice? How is the dimension of the row space and the dimension of the column space related? What's that? Number of rows? I mean, how is the dimension of the row space and the dimension of the column space related? One of the propositions I stated for you guys was that the row space has a basis which is formed from the non-zero rows in the REF of A. How many non-zero rows are there in the reduced echelon form of a matrix? There's as many rows as there are what? Pivot columns, right? What's the dimension of column space? Number of pivot columns. So the dimension of the row space and the dimension of the column space always match. Which is kind of neat, right? Because they seem like different things, right? And yet they're the same. Here's yet another example, a boring matrix. 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, 1. I lost track of how many ones I just said, but you know. And this is a row reduction you'd like to do on the final, right? Yeah? Okay, we can do that. You guys understand that, right? None of you broke a sweat mentally to do that, right? But you understand there are other people sitting to the left and right of you who this step right here would require mental energy at this moment because they have not yet absorbed the first part of the course. And it will continue to penalize them for the rest of the course if they do not fix this. No amount of cajoling and poking will fix it for me, short of corporal punishment, which I'm not allowed. You know, if I could put a shock collar on all the students, right? I could be like, what's the definition? Bartholomew. No one's named Bartholomew, so we can single him out. What's the definition of Bartholomew? Linear independence means that there's vectors in the set. No! Zzz, zzz, zzz. You know, if I could do that, right? Some of you are future school teachers. You need similar things, right? Maybe not a shock collar. Maybe like a little junior bullwhip, right? But the students would wear goggles. I'm not a monster. We don't want to lose the sight, right? Yeah, bring your safety goggles to class so I can, you know. I have many ideas about education. Let's hear. They should invite me as a guest speaker to your education classes. I could offer a different viewpoint. Sorry, I'm digressing. The point is that this has a column space dimension of 1. The dimension of the row space is obviously 1. The dimension of the null space is then what? What? If I know the dimension of the column space is 1, if I know that there are 4 columns in the matrix, what is the dimension of the null space? 3. Without calculation, right? But calculation reveals that the null space looks like this, which gives us this basis. So do you guys have any questions about how to find the basis for the null space, the column space, or the row space of a matrix? Is this enlightening? Have you already figured this out in the homework you've done? Okay, good. I'm sorry, I'm wasting your time. Now, so next up, this I've not covered in class, and I probably won't. But I used Curtis about 3 years ago, and it created much suffering. Much suffering. It's an excellent book. It's just too good. Anyway, I enjoyed it. Students, not so much. But he has proofs of all of these happy, you know, for example, this one, if that's dependent, then if you peel one off and it's linearly independent, what does that say? That says the thing you peeled off must be a linear combination of the things that were already there. You know, every finitely generated vector space has a basis. All right, not surprising. That the number of things in the basis is invariant. We actually prove that, right? You can take a linearly independent set, excuse me, of a set of vectors in V, and you can, if it's not already a basis, you can pick other vectors, say bq plus 1 to bn, to extend a given linearly independent set to a basis. This is very nice, right? And so the proofs of these things are in Curtis, and they're given from a very pure linear algebraic perspective. The proofs in my notes are not so pure. They're much more run through the concept of a coordinate vector, as we saw last time. I will stop talking about things in my notes very soon. So I told you guys this. If V is a vector space, the dimension of the vector space is n. If the set has more than n vectors, it's linearly dependent. All right. If the set has less than n vectors, then that means that the set does not generate V. We did this one in class. I tried to prove it. I'm not sure I convinced you guys or not, but I tried. This is where I'll start next class. So there's going to be some duplication for you guys. Okay, but if we have a subspace of a vector space, then there exists a basis for W. Well, there exists a basis for the vector space, for the subspace, and the dimension of the subspace has to be less than the dimension of the vector space in which it sits. Okay, that's kind of nice. We'll prove that next class. I'll show you examples of it today, though. Proposition 6.68, very natural. This is called the plus-minus theorem in Anton, linear algebra book, which is a great book. Let V be a vector space. Suppose S is a finite non-empty set of vectors. If S is linearly independent, all right, and there's V outside the span of S, then if you take S and take the union of that with V, that's a linearly independent set. This is very nice because it gives us a roadmap for how to extend a given linearly independent set to a larger set, which is still linearly independent. This is a tool for creating a basis. If we have the start of one, we can extend until we get the whole basis, you know. Likewise, if we have a set S which is maybe linearly dependent, right? Well, if we remove a vector from that and its span is still the same, that means that that means that set was linearly dependent, right? So both of these 1 and 2 give us kind of a roadmap for modifying a given set to make a basis. And finally, this is the big one. Well, I don't know if it's a big one, but it's an important one to know about because it saves you a lot of work if you're aware of it. Now, the context is important. If we're in the context, if we know we're in like an n-dimensional vector space, all right? If we have the following three conditions are equivalent. S is a basis. S is linearly independent. The span of S is V. In other words, if you have a set of n vectors in an n-dimensional vector space, all right, if that set is linearly independent, it automatically spans. On the other hand, if it spans, it's automatically linearly independent. Right? But context is so important here. If you don't know that your vector space has dimension n, you can't use this proposition, right? So it comes with strings attached. But often, those strings are attached and we already know them, right? Let me show you an example with, not. So that's more or less it. I mean, I have a smattering of other theorems, which I'll say tomorrow. But tomorrow, right? Well, hopefully tomorrow. We'll see. But here, like, suppose consider is beta t squared plus 1 t 3, all right, a basis for r of t n less than or equal to 2, right? And again, I'm still weaning myself off this old notation. I used to use P2R. What's the advantage of the new notation? Is I'm stating what variable we're writing the polynomial in. So if I wanted to talk about polynomials in T versus polynomials in Pac-Man, I'd have a way of doing that, manifestly with the notation. Okay, anyway, what's the dimension of P2? It's the span of what? 1, t and t squared, right? I mean, that's essentially the definition, right? What was my definition of P2? It's the set of polynomials of the form, at squared plus, well, let's say a plus bt plus ct squared, right? What is that for arbitrary ABC? That is nothing more than the span of 1 tt squared. So this is really, I mean, this is essentially the definition just written in our nice new spanny, that's not really a word, span notation. So what's the dimension? What's the dimension of this guy, the quadratic polynomials of degree at most 2? Well, degenerate, possibly degenerate polynomials was what? Three, right. Okay, so consider C1 times t squared plus 1, right, plus C2 times t plus C3 times 3 equal to 0, right? If we can prove that C1, C2, and C3 are all 0, what does that show? Right, that shows that beta is linearly independent, right? Therefore, it's a basis by the last proposition I stated in the notes. Because we have dimension 3, so if we have a linearly independent set of 3 vectors, it automatically spans. Right? So how do we go forward here? Well, this is really C1 plus 3(1) plus C3 3 plus C2 times t, right? Plus C1 times t squared equal to 0, right? Did I do that right? But remember, we proved linear independence of the monomial basis in class? So we can use that result again, yeah? We have the coefficients of 1, t, and t squared must separately vanish, right? So this implies that C1 plus 3C3 equals to 0, C2 equals to 0, and C1 is equal to 0, right? Equating coefficients, well, by linear independence of 1, t, and t squared, yeah? Thus, C1 equals 0, C2 equals 0, and C3 is equal to minus 1/3 C1, which is, by the way, 0. Hence what? Hence beta is linearly independent, and as the number of things in beta is equal to the dimension of r of t n less than or equal to 2, that implies beta is basis. So let's take a step further. What if I wanted to find the coordinate? If I want to find the coordinates of a particular quadratic polynomial, does this help me? Right, if I asked you guys, what's the coordinates of, say, t squared plus t plus 1 with respect to the beta basis equals to what? See, the calculation we've done so far may not be that helpful. So how should you figure out the coordinate vector for that vector, for example? Do you need to do equations here, or can we just use some, if we understand the definition, right? What does the definition say? What does it mean, the coordinate vector? What does that mean? We're asking for C1 times t squared plus 1, right? Plus C2 times what? T plus C3 times 3 to give us back the given polynomial, right? Do we need to do calculation to see that, or can we just see it? What can we choose for C1 and C2 and C3? In this case, I think you can just see it, right? Maybe I can see it, I don't know. process of elimination, right? Like, yeah, I think this has to be 1, right? Like, that's not up for grabs. In order to create a t-squared, we must use 1 copy of the first coordinate vector, right? So once you use that 1 copy, what's left? That's this piece, right? And that piece. So you told me, Bethany, C2 should be what? Also should be 1. See, that gets what's left, right? And then this better be 0. So, yeah. The coordinate vector of t squared plus t plus 1 with respect to the beta basis is 1, 1, 0. Yeah. Now, what if I asked you instead, find the coordinate vector of at squared plus bt plus c with respect to the beta basis? Now, should you try to eyeball that one? Probably not. But if we're adventurous, maybe we can get away with it, right? Because it's got to be a times t squared plus 1, right? If I do that, I have to subtract a, right? We call this thing v. What's next? I have only one way to get t, right? So I must do plus b times t, right? I'm not. And then plus, how about c minus a over 3 times 3, right? I would say what I'm doing right now would be under the category of clever. Like, I don't think I've ever seen many students calculate this way, right? So I just showed you a trick, I suppose. What's this say? It says the coordinate vector with respect to v is what? A, b, c minus a over 3, yeah? Now, if you didn't do it that way, if you didn't see my trick, how would you have to do this one? Something like c1 times t squared plus 1, right? Plus c2 times t plus c3 times 3 equals to at squared plus bt plus c, right? And you'd read off, you collect things. You got c1 times t squared, right? Plus c2 times t plus c1 plus 3c3, right? We use the linear independence of the monomial basis to read off the following equations. We need c1 equals to a. We need c2 equals to b. We need c1 plus 3c3 equals to c. And you can solve those equations for c1 and c2 and c3 in terms of a, b, c. And you get that. So my cleverness doesn't really save you much calculation. Sometimes you can think your way through things without setting up equations. You guys, too often linear algebra students are a slave to setting up equations because you have an algorithm. You feel like you need to use it. Sometimes you don't need to use it. Sometimes you just need to think for a second and you just write something down, right? It's possible. At times. One more example, then I really will shut up. Find basis for w. Let's look at a new w. W equals to f of x in, let's say, P3 R, such that f of 0 plus f prime of 0 equals to 0. Now, let's think about this. If part of the question is to show it's a subspace, do I want to do the subspace test here? Is that a good use of my time? Probably not, right? Because I also want to find a basis for it. What are you going to do in the process of finding a basis for the space? You're going to produce a spanning set. And at that point, you've proved it's a subspace, right? So technically speaking, unless I try to guide you through it, you don't really need to do subspace test theorem here. So, and you know, a quick gut check will reveal that this is a subspace, right? The zero function plays nice with this equation. And if you have an f and a g which satisfy this condition, then f plus g also satisfies this condition. Scalar multiplication of this gives you, anyway. All right, so what is w? Well, so let's let ax cubed plus bx squared plus cx plus d be in w, right? So I'm going to call that thing f of x, yeah? What do we get? F of 0 is what? D, okay. And what's f prime of 0? Well, f prime of 0 is c. So therefore, what's our equation? We've got d plus c equal to 0. So really, w is what? We've got ax cubed plus bx squared plus cx minus what? C. Because I've just shown that an arbitrary element in W can be rewritten with A and B free, and D is equal to minus C, right? And what is this? Well, let's just backtrack here. This is really C times x minus 1, right? So you can see that this is actually what? Span of x cubed, x squared, x minus 1. So a basis for W is x cubed, x squared, x minus 1, right? And what's the dimension of W? It's 3, right? Now here's a question I have not yet confronted, but I'll ask you now. How would you extend beta sub W to basis beta equal to beta sub W union with some vector, let's say v. Well, let's say g of x, yeah? Such that, beta is basis for P3R, right? And first of all, does my question even make sense? Is adjoining one vector going to make sense? Let's do the counting, right? We've got a 3-dimensional subspace. The universe we're working in is 4-dimensional, right? So we're just missing one building block for the basis of the entire space. So what is that? What is that missing vector? How do you find it? How do you find g of x? Any ideas? Zero, 0, 0, 0, 1. So, okay, so Bethany saw it by inspection. I think that'll work. So if we use that plus, if we use the plus minus theorem, what did it say? If we want to make a linearly, so is beta W a linearly independent set, right? So what do we need? We need, what's our goal? And I think what you said, Bethany, will work. Our goal is to, find g of x, which is not an element of the span of beta sub W, right? That would imply that beta sub W union that g of x is linearly independent So we used thinking. It says g of x equal to what? You said 1? I think that'll do it, because if we go back to the original condition, the constant function 1, derivative is 0, right? But what's the constant function 1 evaluated at 0 is? No, the constant function 1 evaluated anywhere is what? Is 1. So this becomes 1 plus 0 equal to 0, which is not true, which means the constant function 1 is not in this subspace. Yay. So you got that by guessing, right? What's a method of calculation we could use if our guessing just fails us? Yeah.
Why is it just a number 1 and not a vector?
The number 1 is a vector here. It's a polynomial function. Yeah. Vectors in this vector space are polynomial functions. And if you want me to be a jerk about it, 1 is also a vector in the vector space of R. This word vector, it doesn't mean what you think it means. Yeah. Yeah. I mean, how would you describe, I mean, I think you can go back up to the original calculation. To say it's not in the span is just to say what? If you go back up to here, right, we need what? D plus C not to be equal to 0, right? Anything that satisfies that inequation, right? Anything that satisfies that will not be in the span and will be a good candidate for g of x. But I like the choice of 1. All right, anyway. Sorry for blathering on so long this morning. You guys have questions? Excuse me. Man, I wish we had linear in this room. This room is so much better than our classroom. Yes?
So how do we know that that's the only vector that we need to add in to make it a correct basis?
Right. So we proved that the dimension of a vector space is invariant. We know that by definition, 1t squared t cubed is a basis for P3. So it's a 4-dimensional vector space. By the theorem that if we adjoin something outside the span to a linearly independent set, we get a linearly independent set. We know that x cubed, x squared, x minus 1 with 1 tacked on is linearly independent. 4 vectors linearly independent in a 4-dimensional context, it has to be a basis. These are good questions, though. Yeah. Other questions? Yeah.
I think it sort of relates to the other thing.
Yes.
Not like directly though. But why does the ordering of the basis necessarily matter? Because I know it like changes the coordinates, but does that actually matter for what we're doing now?
The order of the basis does not matter to what we're doing right now, right? If you were to take the order of the elements in beta sub w and shuffle them any which way, it would not change the span, right? So, no, in that sense, it doesn't matter. But it does, of course, change the explicit coordinate vectors of given vectors in P3. So in that sense, it matters, in the sense that coordinate vectors would be different if you shuffle the order in the basis, yeah.
But it doesn't actually change the basis, it just changes...
Oh no, it changes the basis.
Or changes
The
like,
basis is an ordered set. So like, for example, if we take beta 1 to be E1, E2, E3, E4. If we take beta 2 to be E3, E2, E4, E1. And if I look at the vector, 1, 2, 4, 6, for whatever reason, right? This is equal to 1 times E1, 2 times E2, 4 times E3, plus 6 times E4, right? And it's also, of course, equal to 4 times E3 plus 2 times E2 plus 6 times E4 plus 1 times E1. So this allows me to tell you that the coordinate vector of 1, 2, 4, 6 with respect to beta 1 is, well, 1, 2, 4, 6. This is not surprising because beta 1 is the standard basis, right, for R4. On the other hand, this tells me that this, by the definition, tells me that the coordinate vector of 1, 2, 4, 6 with respect to the beta 2 basis is 4, 2, 6, 1. So the order of things in the basis does matter. It will change the explicit coordinate vectors. It just doesn't matter to the things you care about in the previous example.
Okay. But it's
Yeah.
still, they both still span the same vector space and still have the same dimension and everything, right?
Right. That's hard to see in my counter response because mine is R4. So it's like, hey, but tell you what, let's make it exciting. This is a subset of R10, right? In other words, I'm missing some zeros. Let me give this a there. I'm too lazy to write all the zeros here. I guess I'll manage over here. 1, 2, 3, 4, 5, 6. I mean, yay, there we go. So this is a 4-dimensional subspace of a 10-dimensional space. These are two different choices of basis. Of course, different coordinate vectors, right? But reshuffling the order of the elements in a basis just it changes the coordinate vectors and changes span. Now, I guess I could ask you this follow-up question for my silly response to Bethany's question. How would you enlarge beta 1 or beta 2 to a basis for R10? I claim any subspace you can take a basis for a subspace and you can always extend it to a basis for the whole space. This is a theorem I'll try to prove next class. Right, E5, E6, E7, E8, E9, E10. Right, we're done, yeah. Not exciting, but yeah.
So when we have only 4 vectors and it's a subset of R10,
Yeah.
then what did you say that was? Like we have to add 6 more to make it a basis. So what is it if there's only 4?
So W, oh, very good. So W would be the span of beta 1 or beta 2, whatever you like, right? So the dimension of W in this context is 4, right? If we take beta 1 and we adjoin E5, E6, E7, E8, E9, and E10, then that would be beta, this would be actually for all of R10. So it's a 4-dimensional subspace of the 10-dimensional space. To get a basis for R10, I need to adjoin 6 vectors which are outside of W and which are also linearly independent with respect to each other. Yeah. I mean, this example is more fun if you do something like this. W is, let's say, A in R3 by 3. such that the trace of A is 0. This is the set of traceless 3 by 3 real matrices. How big is R3 by 3 as a vector space? What's the dimension of R3 by 3 as a real vector space? What's the basis for R3 by 3? Do you guys remember? E11, E12, E13, and so forth and so on until we get to E33, right? 9 of these. So this is a 9-dimensional space, right? Traceless 3 by 3 matrices, it's what? It's a 9-dimensional, the parent space, right? The vector space, V, if you like, is R3 by 3. So you guys tell me, intuitively speaking, the trace is, what is the trace defined to be? This is not intuition, it's in your homework, right? What's the trace of A? Sorry. Sum of the diagonals, which in this context would be plus A22, yeah, A33, right? So, point being, if A is in W, right, then A equals what? A11, A11, A11. Oh, wait a minute. That's not right. Let's see here. If I set that equal to 0, what should I do? I maybe solve for A33? I don't know. What's A33 equal to? So I should really put, instead of A33 down here, I should put what? I should put minus A11 minus A22, yeah? What about the rest of the entries? There's no condition on those at all. They're just, as usual, A12, A, you know. So there you go. That's a generic element in the subspace. If you can write down a generic element in the subspace, you can find the basis for the subspace. That's what I did in the example over here. That was my strategy. I took the equation which defined the subspace, right? And I found a way to write an arbitrary element in the subspace in terms of a minimal set of parameters, right? And that revealed, that it was a span. I guess technically speaking, I also need to know that these are linearly independent, right? So there's a small gap in the solution, really, if you want to be picky. But it is fairly clear that these are linearly independent, so I don't feel too bad about it. Here, so what if you were to write this out in terms of, what is this? This is like A11, right? E11 plus what? Well, I'm getting tired of writing that, so let me just write it out this way. This is the sum, I not equal to j, right, of Aij, Eij, right, plus what? A11, E11. Why did I put, come on, guys. That's no bueno. This is 2, 2. So A11, E11 plus A22, E22, right? Plus minus A11 minus A22, E33, right? So what's the basis for W in this case? At this point, you should be wondering, why on earth did you not do the 2 by 2 case? I don't know. I'm too far in. E12, E21, E12, E13, E21, E23, E31, E32, E11, E22. Uh-oh. No, no, no. That would be bad. Can these be part of a basis for W? Can you have something in the basis for a vector space, subspace, which is not actually in the subspace? No, because the span allows 1 times the vector to be in the span, right? So if the vector was not actually in the span and you say that it's part of the generating set, you're in trouble. E11 is not traceless. What's the trace of E11? 1, yeah. Is 1 0? Yeah, not usually. So what I have to do is I have to pay attention to combining, right? So it's A11 times what? E11 minus E33, right? And it's A22 times what? E22 minus what? E33. And see, those differences are good because diversity matters. Let's see here. No, because we want correct math. Diversity doesn't matter here. Oh, I'm sorry. Diversity always matters. What am I saying? Let's see here. E33. Oh, there we go. So what's the dimension of the set of traceless matrices? Eight. There's 2 ways to see that. The one is just directly from the definition, counting. 1, 2, 3, 4, 5, 6, 7, 8. The other is a sort of more intuitive calculation, which is I'm starting with a 9-dimensional context. I'm imposing one real scalar equation. 9 minus 1 is 8. To give you a different example, which might be your homework question at some point, but I don't care. If we had W, say A in 3 by 3, such that A transpose is equal to minus A. So this would be the subspace of skew symmetric matrices. I told you guys before, at some point, that if the matrix is equal to minus its transpose, it says something about the diagonal. What does it say about the diagonal of the matrix? They're what? What do you say? Own it.
I said it's 0.
Very good, yes. Because, what does this mean? A transpose II is equal to what? Minus A II, but what's this? It's AII equal to minus AII. Therefore, AII is equal to 0. Yeah. Supposing we're not working over characteristic 2. And I said we're in the reals, so, okay. This is a matrix equation, right? So a matrix equation is actually 9 equations at once, 9 scalar equations at once, right? So shouldn't the dimension of W just be 0 because we're starting with a 9-dimensional context and we're imposing 9 equations? Shouldn't there just be 0 dimensions left? What's wrong with my thinking? I mean, this is a matrix equation, right? That says that AJI is equal to minus AIJ for 1 less than or equal to I comma j less than or equal to 3, right? That is 9 equations, but they're not. The rub is that they're not independent equations, right? You have 3 equations which essentially say that the diagonals are 0, and then you have 3 other equations which say what? The off diagonals match up by a minus. So that if you really study the equations, there's really only 6 independent equations here, which means we should expect that it's a 3-dimensional subspace. But that aside, if we have, A, B, C, D, E, F, G, H, I is an element of W, then what can you tell me about that?